This lecture is going to be a bit convoluted because it covers a lot of materials, but I want to try to finish this within 2 hours. So I'm a little undecisive on what to cover. All right, but that's perhaps it'd be good to first start with let's start with quantum spin. All right. So we know that in NMR we have, this is NMR. NMR stands for nuclear magnetic resonance. Okay. And here we have usually in an NMR setup, we usually have a static B field and nuclear spins on molecules. Okay, so you usually have like a molecule that looks like, I don't know, weird shape, something like that. Okay, and on one of the atoms you have on the atoms you have the nuclei, right? And some of the nuclei have a spin, a net spin. Okay, and that spin can respond to, that spin of course is the electron, no sorry, it's the nuclear spin, and it is spin 1/2. Okay, similar to electrons. So it will respond to the external B field. It will align with it as its lowest energy state. Okay, the energy is minus U dot B. Okay, well, the thing about nuclear spin is that it has the same sign. The magnetic moment and the spin has the same sign, but for electron spins, they have opposite signs. Okay, that's just something to keep in mind. Okay, they are both 1/2 spin, but they have the spin and the magnetic moment have different signs for nucleus and nuclear spins, and have different signs for the electron spin. Therefore, for nuclear spin, the lowest energy state is for the moment, which is a vector represented by this arrow. Then the lowest energy configuration is for the spin to align with the field. So the inner product is a positive number. Okay, and so this will be a ground state, and going down will be an excited state. All right. For the electron, is the opposite. Pointing down is the ground state. Pointing up is the ground state, and pointing up is the ground excited state. All right. So just know that. But today our goal is not to talk about NMR or nuclear spin. Our goal is to talk about the quantum spin. Okay, so I want to explain where does the analogy come from, because we use the word quantum spin for a lot of things, not just limited to electrons or MV centers. We also use it for atoms. Okay, and if you do not understand the context, it could be very confusing, because in atoms, there's no magnetic moment going around, rotating, processing. There's no such things. So where does that terminology come from? Why does it apply to even atomic qubits? Okay. All right. So to to go into our discussion there, I want to give you two basic, I want to explain two basic physics about a nuclear spin in the magnetic field, okay? First of all, the nuclear spin, first of all, yes. So this is a larger picture, a zoom in picture. This is the ground state. Okay? This is the excited state. Yes? Okay. Now, if I have this, so you know this direction is the high energy state, and this direction is the low energy state. This is low energy. This is high energy. Now, if I make it not go 180 degree, but just go, say, 30 degree to the side, okay? What will happen? It will go back to the ground state through the action of the magnetic force. Okay, that would be a reasonable guess. But you understand that Lorentz force, the magnetic force, originate from the magnetic force originate from the Lorentz force, correct? At the microscopic scale, the magnetic force originate from the Lorentz force. And for the Lorentz force, we all know that it has the formula of V cross B. So F equal to V cross B. Therefore, such force is always perpendicular to velocity. So it cannot do work, right? Because work or the power is V dot force. Yeah. So overall, we know that magnetic force cannot do work. It cannot change the energy of the system, either on the microscopic scale or on the macroscopic scale. It just cannot change the energy of the system. Yeah. So if this thing will rotate back to its ground state, then the energy is changed. Well, that will violate this principle of magnetic force not doing any work, cannot do any work. So this cannot happen. All right?
It will rotate in that angle?
Yes. So rather than changing angle in this direction, you will change angle in the azimuthal direction. And this will count as an equipotential trajectory. You'll do this. Okay? Because when it does this, the energy which is associated with theta is unchanged. Right? Yeah, so any fluctuation that it has will only push it to go to, you will wobble around this equipotential trajectory, but you will not go like this, okay? And to be more precise, the equation of motion for a magnetic moment in the field is this, okay? So you can see that this is the magnetic force, and this force, you can do a cross product, right? From the magnetic moment to the B field, to the interaction between the magnetic moment and the static B field. You will have a force that points this way, out of the board, and then when it move a little bit, that force will change its directions, a little bit like the centrifugal force. Okay? All right, so this is the first thing, precession. Okay? All right. Now, the second thing is, in NMR, they manipulate the nuclear spin motion not through this static field, not by changing the static field. But they have an external field that point this way. They have an external field that point this way. Okay, B external. They have like an additional field that point in the perpendicular to the static field. And it is this field that can be used to change the energy of the spin. Yeah, why is that? Because we said that magnetic force should not be able to change energy, right? So why can this be used to change energy of that spin?
That's perpendicular to it.
Hmm? Well, when you have a spin, let's start with, okay, maybe we can start with this too. So when you have the spin in the tilted, of course it doesn't matter if it's tilted or not, but I'm using this as an example. When you have a spin that is tilted, on top of this precession motion, which is given by the static field, you will also feel a magnetic force from the B field, from the B external, right? And here, this the spin will try to precess around the external field as well. Yeah? And that trajectory is this. Right? So let me maybe just put it like this. B external. Okay? By the way, there's the rotation, the sense of rotation is according to the right-hand rule, but with your thumb opposite to the magnetic field. All right, so it's this. Okay, and here it is this. Okay. All right, so this is the trajectory we will follow with respect to the B external, right?
Shouldn't it be the other way for blue rotation?
You mean this way?
Yeah, the blue should the blue arrow pointing down.
If the blue arrow, no, the motion.
Yeah, it's the other.
Yeah, the motion will have a normal vector. The normal vector determined by the motion, by the rotation of the motion. The normal vector is opposite to the B field, according to this. Okay.
That's right.
That's fine. All right. So yes, this is the equal potential trajectory with respect to B external, but it is not an equal potential trajectory with respect to the static B field. You see that? So I can, of course, turn this on for a moment, rotate it, and make it go to this direction, right? And then I stop. I turn off my external field. And at that moment, this will start to precess again around the static B field, right? In the same direction. In the same direction as before, okay? But you see that my theta, my polar angle has changed in this case, Okay, so these are the these are the two things we want to. These are, I guess, as a background knowledge. These are the two things I want to mention, and this is the two things concerning the spin dynamics in the B field, in the magnetic field. All right. So let's go to the quantum spin. Okay, for quantum spin, when we talk about quantum spin, we usually are referring to two-level system. Okay? Or you can call it a qubit. Okay? Bit means 0 and 1, right? Two-level system. That's 0 and 1. And it's a quantum system, so it's a quantum bit qubit. Okay? So quantum spin, usually we refer to the two-level system. Why is that? Well, here's the reason. Well, we know that any quantum state can be described. For a two-level system, any quantum state can be described with two coefficients of the ground and the excited state. Correct? All right. Now, there are these two coefficients, these two probability amplitude are not completely random. There's a constraint, which is that the sum must be 1, right? The probability must be 1. There's one constraint. All right. So there are so these are two numbers, two complex numbers, but they are 4-degree freedom, right? The real and the imaginary part of CG, the real and the imaginary part of CG, right? So they are like four free variables, free parameters with one constraint. So how many free parameters it leaves us? 3. Yeah? So in principle, we can try to write this in another form, which is phi, and so in terms of amplitude and the phase, right? We can write it as this, G and E phi, right? The cosine and the sine are just given by this equation, okay? I have not given any physical interpretation or any meaning. I'm just saying from the 3 free degree of freedom, 3 free variable, independent variable, we can parameterize CG and CE using theta, G, and E. Sorry, theta, phi G, and phi E, right? All right, so that's good. Yeah?
We have to take into consideration that the state should be orthonormal in this case.
The state, yeah, the state is orthonormal. Yeah, this is the orthonormal condition.
Okay,
yeah. They are orthogonal already, of course.
And
this is the normal condition. Yeah. So the normal condition gives this. Okay, so it simplifies 4-degree freedom into 3. Okay, that's the first thing. The second thing is when we do measurements, for example, when we do measurement in our spin lab, we're interested in the population on either the ground state or the excited state, right? So usually we want to find out what is this as a function, say, of t, or as a function of w, omega, right? We want we want to find out what is this, right? So so how do we calculate this? Usually we just take the modulus of CE. But where does C come from? Of course, C, let me just use T, for example, as an example. Where does CET come from? It comes from, this is the probability amplitude at a specific time T. Okay? And this comes from your initial state evolved on the, say, a microwave pulse. Right? So remember our Rabi solution, like this very, very long solutions. Usually it looks like this. I'm not gonna write everything out, but basically it looks like a lot of coefficients times CG 0 and another coefficient times CE0, right? Okay, this is my simplified version of the Rabi solution, and CG is the same. And this is, I see. Okay, I hope you understand what I'm trying to write here. Okay, so these are just like a bracket for fill the coefficients. All right, so usually has two contributions. The excited state can be achieved. So this is CG0, this is CE0, a time 0. And at a certain time later, CE have contributions from CE0 and CG0, right? And so is CGT, it has contribution from both. Okay, that's what this tells us. All right, so so we know that this has, so usually the observable of our interest have contributions from both states. CG, so let me just write this, and CE. Okay. Now, would it be better if I just use A and B? Maybe better if I just use A and B. Maybe easier to write. So this is A, this is B, this is A prime, this is B prime. Okay? So A, this is A, this is B. Okay, now we are all familiar with this, right? When you have two terms in the modulus, then you have the self term and you have the cross term. These are the self terms. And these are the cross terms. Okay. Why am I writing this? I write this because I want to point out one thing. In the measurement, what matters to us the most is the cross term. And the cross term is a product, right? and the cross-term is a product. And of course, this matters to us too. But this term does not carry the phase information from CG. Okay, let's say my initial state. Okay, my initial state is described. Okay, let me just put this 0 here. So I'm using this 3 parameter to describe my initial state. Okay. So the initial state, the information or the configuration in my ground state phase and my excited state phase does not matter for the self-turn, right? Because they're just whipped away by the modulus. Yeah, only theta, only the amplitude turn is left. Okay. But for the cross turn, the configuration, the state in the phase does matter. Like the value of the ground state phase and the value of the excited state phase does matter. So in other words, the self turns are not phase sensitive, but the cross turns are phase sensitive. Okay? So the cross turns are phase sensitive. Therefore, your result will depend on your initial orientation, right? So if we see this as like an azimuthal angle, and this as a polar angle, right? It matters a lot if CG is this or this. The results are very different. Okay. The result, the phase of the ground state change the result through the cross turn. Okay, the cross turn is phase sensitive. But since it's always a cross turn, sorry, I have, yeah. Since it's always cross turn, I have the sum. I always have the sum of the two phases, or rather the difference of the two phases. Correct? The phase turn matters, but always through the difference. Okay, you see that? All right. So that what that means is it's very similar to the potential energy where the offset doesn't matter, but the potential energy difference leads to the force, which has a physical effect. The same in quantum mechanics. The absolute value of the phase does not have physical significance, but the difference, the phase relative to what, right? The relative phase has a physical consequence. Okay? All right, so therefore, this condition, or in a more formal term, this is a gauge invariance condition. This is called gauge invariance condition, right? But not just stay with the physics, okay? The physics tells us it's always the cross turn that brings in the phase information, and the cross turn is always a product of the two turns, and you always have and the product is something with something conjugated. So you always have the difference. So it is the difference of the phase that matters. Therefore, we might as well just define let me rewrite this. Okay. So I want to write it like this. Okay. we might as well just define a parameter that characterizes the phase difference, the relative phase, between the excited state and the ground state. And we just use that for the excited state and make this go away. Yeah? So this gives us a further simplification. So we go from 4 to 3, now to 2 parameters, theta and phi. Yeah? All right, so I'm trying to go with this is quantum mechanics, the quantum state can be described by 2 parameters, theta and phi. Okay? And, and if you have a keen eye on geometry, you probably could recognize that this can be cast into a geometric interpretation, which is the polar and the azimuthal angle on a sphere. Okay? So when we learned classical mechanics or classical electrodynamics, we have learned about this polar angle. The polar angle is theta characterizes the angle between your vector on the unit sphere with the z-axis. And the azimuthal angle is your projection, the projection of your vector on the xy plane, the angle between that and x-axis, right? Okay. So Feynman, I believe it's Feynman. Feynman gives this interpretation, this geometric interpretation of the probability amplitude of a quantum state. So he mapped this state coefficient through, this series of reduction to 2 real parameters. So two complex number to 2 real number, and that 2 real number represent the angle, the polar and the azimuthal angle of a unit vectors. And that unit vector is called, for some reason, this is called the Bloch sphere. This unit sphere is called the Bloch sphere, and this thing is called the Bloch vector. Okay? All right. So Bloch vector characterized by pi and theta. Now, why does this have to do with the spin? Well, first of all, we can see that the ground state is characterized by theta equal to 0, right? If you theta equal to 0, you have the highest in the ground state, and you have 0 in the excited state, right? So that's the north pole. And the excited state, in principle, it should be, it would be nice if the excited state is described by pi equal to, theta equal to pi. Oh, but this doesn't work, right? Because here we have sine theta. So if we put pi here, it is still 0, and that's still the ground state. All right. So, but that analogy could work if we just simply start with, pi theta over 2 here, which is equally valid according to the normalization condition, right? So which is equally valid. So If we start with theta over 2 as our parameterization, just as a mathematical convenience, then we can have this block vector point to the north pole as the ground state of the nuclear spin, and pointing the south pole as the excited state of the nuclear spin, right? So that would be nice. So that's the first connection. If we construct our probability amplitude as this, then its geometrical interpretation mimic the nuclear spin. But here we don't really have a spin. We have just a two-level system, and this two-level system can have a magnetic nature or electronic nature, right? So in an atom, we have different electron energy eigen levels, electron energy eigen states, right? So if we isolate, we can somehow manage to isolate two of them, then that's a two-level system. And there's no physical spin that does this, but we can still describe that quantum system with this picture, okay? And now with this mathematical construction, we can map it at least, you know, with the north pole and the south pole corresponding to the ground state and the excited state. So that is a very interesting correspondence, and that's nice. But they are more. But the analogy, the analogy, the connection is far beyond. It turns out to be far beyond, you know, far beyond this. People who have studied this system found that even the dynamics of these block vectors. So you can see, since the theta and phi describe every point on the sphere, you can see the sphere itself as a 2D Hilbert space, right? It's just curved, but it's a 2D Hilbert space. So the dynamics of the quantum state vector on the Hilbert space turns out to have exactly the same equation, to be described by exactly the same equation as a nuclear spin. Okay, therefore it's called isomorphism. In mathematics, it's called isomorphism. Anybody recognize this term?
I heard it before, but
yeah. That just means the two systems have one-to-one correspondence. Whatever happens here happens there. They are equivalent. Okay. So it just so turns out that when we express our state in such a way and have a geometrical interpretation like this, then even the dynamics is equivalent to the nuclear dynamics. Therefore, that's why we call a two-level system quantum spin. Okay? But know that there's not a physical magnetic moment that is turning around like in the case of nuclear spin. Okay, that's the first thing we want to cover. All right, so let's take a quick break, all right? 5-minute break, and then we'll come back to optical block equation. To save some time, I will write down the equations on the board.
And the external battery is the white one.
Yeah.
Sure.
Yeah. Just remember to press the button when you set it up.
The 三用电表 is not.
Multimeter.
Yeah, it's not in the lab.
Go ask. You know who the technician is?
I know, but I don't know where she is.
Her office is on the 4th floor. On the stand, just right below files 6.
Okay.
Also, I think they are 4 or 5. Yeah. So look for her there.
Yeah, and there's something weird with the alignment laser on the small table. The signal is oscillating in a weird way,
like last time, right?
It's not only the T and A is oscillating. It's like A and B also quite oscillating.
Yeah.
I'm not sure why.
I think it's again the reflection issue. Have you tried to get the filter? Is there a filter? Yeah, is there a filter involved?
Yeah.
Okay, so maybe try to just get the filter aimed at a different angle and see if the oscillation is present in T, then it will be present in everything, in every other detector. Yeah, because that is the interference between some kind of reflection and the input beam. So you just need to, yeah. Okay, see, just like what you did last time. And see,
last time you asked me to turn the angle of the x-column.
Right, and so now without the acetone, does it? No, sorry. So without the filter, does that weird oscillation show up?
I'm not sure because without the filter, it was different.
Right. True. You could try to put the filter because the mount can be moved, right? You can put in front, just like directly, in front. Yeah, or you can put it in front of the in between the two mirrors, just to see if that's the reason that caused it. Yeah. Okay. All right. So what we're gonna cover next is a bit technical, but I think this is necessary to understand what's going on. So we have all seen this, right? The Rabi model. The Rabi model is valid for a time that is between the poles, within the duration of the poles. We can write out our equation of motion, Schrödinger equation, as this. Okay, Eg and Ee represent the energy of the two states, and h bar omega naught is the difference between them. So h bar omega naught is the difference between Eg and E, right? And here the V describe the coupling, which is caused by our external our microwave or our external perturbation. Okay? Now, I want you to know that without our external perturbation, if we only have this unperturbed part, the unperturbed Hamiltonian, the solution is actually quite simple. the solution is that A, E will just be rotating at a frequency of G. Okay, so omega G is EG over H bar. So I'm sorry. This is E, this is G. Okay, so this is like without any external perturbation. If you just like set your state at a certain initial state, and you just let it freely evolve. This is the solution. Okay, and if we cast this into this form. If we cast this into this form, you can see that this is basically, since we're using the relative phase, so this is basically AG G times AE times the phase of the excited state is omega ET. Okay, so this is omega E minus omega GT. Okay, the relative phase difference, right? And of course, this is just omega naught, the energy difference. Okay, so this is the free evolution. This is the free evolution solution of a two-level quantum system. You can see that the geometric interpretation here is that, of course, if you are in the ground state, you stay in the ground state. But if you are tilted away from the ground state, from the z-axis, right? If you have a little bit of an excited state, so that theta is not zero, theta is a finite non-zero value, then you will start to have this phase turn coming in, right? And what is this phase turn? This phase turn represents the angle between your vector and the x-axis, okay? And this angle takes a minus value, right? So what it does is it will rotate, okay? It will rotate clockwise. You will rotate clockwise. You'll rotate clockwise in the box sphere, okay? That's the free evolution. If you just have a little bit of deviation away from the z-axis, you will have this, okay? The black vector will do this. And this is the same as the free precession of a nuclear spin in a static field, right? That's why I told you that even the dynamics are the same, right? So when I was given two features of the spin dynamics of the nuclear spin, I said there are two things: the precession, the free precession, and there is this excitation, right? So how does the excitation work for a two-level system or for a black vector? To see that, we need to go through a series of transformation, okay? A series of transformation of the equation in order to see that, okay? And that's the confusing part because in a lot of textbook, these steps are kind of omitted, and so they are like people are presented directly the optical block equation, but they don't know that they are actually a series of transformation involved in between. So like where is the optical block equation appropriate? Where can it be applied? That all the pre-assumption, all the conditions has not been explained or not been set, not been well defined, and that could cause confusions in your interpretation of your data. Okay. Because after all, your data, the data you took is in the lab frame. Yeah. All right. So that's why we kind of have to go through this trouble of changing frame, and I'll explain what this is. Not in great detail, but I just want to give you a gist of it. All right. So coming back to this. So I said that this unperturbed Hamiltonian will give you a free precession motion, right? And what about this? What about the interaction? What will the interaction do? To find out what the interaction will do, it will be helpful to simplify our equation a little bit by simply since we know the unperturbed part is nothing but this. So we just kind of redefine our parameter to incorporate this free precession, okay? If we do that, then the coefficient that we are looking for no longer include this free precession, yeah? And the free precession, the unperturbed Hamiltonian term can be removed from the equation. This is the so-called rotating frame, okay? And I call it rotating frame. Remember, here's a minus sign. I call it rotating frame omega naught. Under this rotating frame, the unperturbed Hamiltonian can be removed, and only the interaction term is left. That's why this is also called the interaction picture. Okay? That's why I have a little subscript here, interaction picture. The wave function under the interaction picture or under the rotating frame omega naught. Okay? And when you write down every term, you will find that there are terms like plus minus, sorry. There are terms like omega plus minus omega naught t. Okay? There are terms like this. Okay? And from our discussions in parametric excitation, we know that in order to achieve resonant excitation, you need to have that whatever is oscillating in your drive to be zero, to be as close to zero as possible, right? Because when we remove the unperturbed Hamiltonian, effectively we are saying that our resonant frequency now is zero. So in order to be resonant to zero, in order to be resonant with the zero resonant frequency, we want this drive term to be as close to zero as possible. Therefore, we drop the high frequency term, which is omega plus omega naught. Okay, omega is the drive frequency, and omega naught is the system frequency, is the system oscillation frequency. Okay, so omega plus omega naught is a large number. That's far from 0. So effectively, we can drop it without affecting our dynamics too much. Okay. In fact, if you run a computer simulation and you include this, the only difference you will make is just little wiggles on your probability trajectory, just a little wiggles, very fast wiggles. But the trend is determined by the difference term. Okay. Therefore, we can safely drop the high frequency term, and this thing, this practice is called the rotating wave approximation, RWA, rotating wave approximation. Note that this is different from rotating frame. Okay, these are two different things. Rotating wave approximation and rotating frame are two different things, and they are used in different occasions. Just in this case, we are using these two things together to achieve a simpler form of the Schrodinger equation. Okay, so this is Schrodinger equation we mostly care about, and this will describe how the interaction affect the probability amplitude. By the way, here I introduce this chi. Here the chi represent, maybe let me write it here. Here the chi represent the coupling. Okay, so it's basically proportional to how strong you pump it, how strong you drive it. That's all. Okay, and of course the transition coefficient, which is intrinsic in the system's wave function. Okay. All right. So this is the equation of motion we will start with. Okay. Now, in order to find out the dynamics of the quantum spin, we need to somehow find out the equation of motion for theta and phi. Correct? Yeah. So how do we do that? Well, there are 2 steps we need to take. The first step is to switch from the Schrodinger equation to the density matrix formalism. That sounds like a very scary thing to do, but it's actually easier than you think. It is just a little cubism, right? But it's doable. Right. So what is a density matrix? A density matrix is defined as a tensor product of your wave vector. Okay? So what does this mean? This means this. Here, we write our state like this. Right? CGCE. Right? This is, if you take this G as 1, 0, and this E as 0, 1, this is linear algebra, right? Then you have CG and CE. Okay? And this is its Hermitian conjugate. So it's CG star and CE star, right? And this represents the tensor product. Okay? And what is a tensor product? A tensor product is basically just distribution. So this whole thing, you take, so unlike the dot product, you take the whole thing and you multiply by the element, by the individual element, okay? So it's like this, CG times this whole thing, CE times this whole thing, okay? And then, and you keep the space. So this becomes CG star, CE, CG star, C star, CG, CE star. Okay?
Why do we have to do tensor product here, since it's the same state, we can directly do the matrix multiplication?
Sorry?
Since it's the same state, we can do the matrix multiplication instead of tensor product, right? In this case, density matrix space.
I don't understand what you're saying. What's your question? Why do we need to use tensor product? Or why do we need to use density matrix? Those are two different questions.
No, I mean density, bra and ket, you can directly use matrix multiplication since it's the same state, right? You don't need to use this.
No, you have a column vector, you have a row vector,
Yes.
okay? And there are different operations you can do with a column vector and a row vector, right? You have, of course, the dot product. We all are familiar with what that is. But you also have this thing called the tensor product, which is defined as a specific series of operations, okay? This is just how the density matrix is defined, okay? Don't worry about it. If we define something called the density matrix as the following, okay? Then the density matrix will have is a 2x2 element then the density matrix is a 2x2 matrix whose elements is composed of CE, CG, CE star, and CG star, okay? Now, the reason why we want to use this formula will become clear later, okay? But I want to point to you that here you have the population on the diagonal terms, right? So this is basically CG modulus square, and this is CE modulus square. On the off-diagonal element, you have the cross term, right? You have the cross term. And remember in our measurement, the example I just showed you, PE, right? Probability of the population in the excited state, right? We have the self-turn, which is not phase sensitive. We have also the cross turn, which is phase sensitive, right? The phase sensitive cross turns is composed of the product of CE and CG conjugate, right? So that shows up here in the off-diagonal terms, okay? So in a way, you can say that a density matrix takes the self-terms, okay? There were four terms in our observables, right? There are four terms in our observable. Two are the self-terms, two are the cross-terms. The density matrix takes the four terms as individual matrix element. You see that? The self-terms, the two self-terms are in the diagonal element. The two cross-terms are in the off-diagonal element, okay? And the formulation in this density matrix formulation is meant to track the dynamics of these photons individually. Okay? In other words, we want to know how does the cell turn evolve. Like, we want to just like cut through the throat. We want to know in the observable there are photons, and how are these photons evolve. We don't want to start with the probability and the state. We want to like go straight to the observable, and we want to know how the observable turns, the constituent of the observable. How are they evolved? So these are the cross turns. These are the cross turns in observables. And these are the self-turns. I call it self-turns in observable. Okay, we want to know how they evolve. That's all. So, can we do that? Answer is yes, of course. We can do that because we know the basic equation for CG and CE. Then, of course, we can figure out how the product turns evolve. Okay. All right. So here I'm gonna write this as. I'm just gonna call this following the mathematical convention, G. So I'm using G and E as my index, right? So here is EG, and this is GE, and this is EE. This is just the same as the mathematical convention, okay? In mathematics, we have 1, 1, and 2, 1, and this will be 1, 2, and this is 2, 2. Okay, and now I'm using G as 1, E as 2. All right. Okay, so we use this full matrix element to represent this four product turns. Okay, and these four product turns correspond to the cross turn and self turns in observables. All right. So now, if let me just do this to show you how this is typically done. So if you want to find out how does this turn evolve, okay, then this is nothing but CG dot CE dot CG star, right? This turn is this turn, and the time derivative of this is just time derivative of this and time derivative of that, yeah? And the time derivative can be found here. So you just plug it in. And we will do a little simplification in our notation. So here, this will just use delta. Okay, we'll just use delta to capital delta to represent the frequency difference. So here we have the delta. CG star. Okay. So at the end, you will see you're always guaranteed to have products, right? You're always guaranteed to have product terms. So Okay, so not too hard, right? The time evolution of this depends on these two parameters. Okay? And the time evolution of this is, since this is the complex conjugate of this, you can just take the whole equation as a complex conjugate and you get equation for this, right? So that is already given. And here, this is also pretty straightforward. I'm just going to give you the same procedure. I'm just give you the answer here. Okay. All right. So it looks like this. The evolution of GG, rho GG, depends on the two off-diagonal terms, rho GE and rho EG. Now, this looks like very much more complicated than the original Schrodinger equation, right? Because now, by the way, these are all real. Oh, sorry. This is a real number, this is a real number, this is a complex number, this is a complex number. So not only we have 4 complex number now, no, sorry, two complex and 2 real. We have more variables, so more equations. It's even longer, right? So on the first sight, it doesn't seem that this is very useful. Okay. By the way, let me just write. So PGE, the equation of PGE is just the whole equation here. You take the complex conjugate. Yeah. And so we're given rho GG, the equation for rho GG. How about rho EE? Rho GG and rho EE are related by the normal condition, normalization condition. So we know that rho GG and rho EE add to 1. Therefore, rho EE is minus rho GG. Okay? Yeah, so you take the complex conjugate of this, you get the dynamical equation for this. You take the minus sign, you put a minus sign here, you get dynamical equation for this. Okay, so you have here all 4 equations. Okay, so I won't repeat myself. But what is the big deal here? The big deal here is the big deal will come in a minute. But we notice that in this equation, it will be very nice if we can give me a second. Okay. it'd be very nice if we can somehow get rid of this time dependence. Sorry. You see this time dependence? Right? When you solve a differential equation, when there is a time dependence, it is, I think it's called like an inhomogeneous equation. It's harder to solve. But if you can get rid of the time dependence, it's easier to solve, okay? That's what I want to say. So if you see like this thing, exponential I or exponential I minus I delta t or exponential plus I delta t all over the place. It'd be very nice if we can get rid of them, all right? So in order to do that, we want to do yet another transformation. And here the transformation looks like this. We want to replace this by something that has a minus delta t dependence. So if you replace this rho Eg with rho Eg prime times exponential I omega t, then this minus I omega t and this plus I omega t will cancel, right? And they'll be removed. All right, so and this will also take care of this problem here because you have rho Eg on this side. So just by just by making this assumption, not the assumption, not assumption. This is just like this is just like this. You redefine your parameters. You include the time dependence in your variables. By defining this, you can greatly simplify your density matrix equations again. And this is yet another rotating frame. Rotating frame. And now here we have the minus delta. So I call it rotating frame delta. Yeah? So this is rotating frame delta. And if we do that, the equation of motion could be greatly simplified. Okay. So now instead of this is the density matrix. In the rotating frame, okay? Omega naught. Now here we have a density matrix. G, G, E, G, G, E, prime, prime, E, E. You have a density matrix. Density matrix. So this is rotating frame omega naught. This is rotating frame delta on top of rotating frame omega naught. Okay? And delta is omega minus omega naught, right? So effectively, this is actually density matrix in the rotating frame, omega. Okay. All right, so this is the connection. This is not explained in most quantum optics textbook. A lot of times they just start with rotating frame omega and you don't know why. Like, what is so fundamental about omega? Because omega is a variable. You can change it, right? That's your microwave frequency. You can change it. So why do I want to choose something that is varying and put all my equation with respect to that? It's very confusing. Here's the reason. There are actually 2 steps instead of 1 step. You first go to the characteristic frequency. You first go to the rotating frame according to the characteristic frequency of the system, omega naught. And then, because you want to simplify the equation of motion of density matrix, so you want to go in yet to a second rotating frame on top of this, and that is delta. And because the delta is omega minus omega naught, so effectively they together. This can be proved mathematically, but you just have to take my word for it. This is effectively it's rotating frame omega. Okay? In this frame, you see, you don't have any time dependence. Very nice. Okay? What's more is it's the second thing. There's for a 2x2 density matrix, you can have linear expansion, just like in linear algebra, you can have a base, and that you can have like an orthonormal base, and that expand every vector, right? For a 2x2 matrix, you can do the same, okay? But now the base is called the Pauli matrix. Yeah. Now, so if you do the expansion using the Pauli matrix, so the basis is the Pauli matrix sigma x, sigma y, and sigma z, and u, v, w are the expansion coefficient, all right? And you have like 1. 1 is also part of the base. Then here I'm gonna write down Pauli matrix. So this is, I think, oh, sorry, wrong. Okay, so this is the Pauli matrix. Then this become sorry, I'm gonna have to put the 1/2 vector is just to make everything more symmetric, more like nicer, looks nicer. It will look like this. Okay. If you expand this as a Pauli matrix, then the 4 elements that you have in the density matrix can be represented by U, V, and W. Okay. So here you can see U and V are basically the real and the imaginary part of the cross terms, right? This is just the conjugate. And W is basically how far this is away from half. Because remember, they must add to 1, right? So the average value of you will expect for, like normally for PG, rho GG and rho E is half. So how far they are away from the average value, okay? If one goes up, the other will go down. So that's the W, Yeah. So it basically calculate. It basically bear the meaning of of the population difference, right? So here, I'm just gonna write it. E.g. V E.g. G E E. Okay. So you can see the W has the physical meaning of the population difference. But noted that it is the population difference of ground minus excited. In our experiment, in the ODN, in our experiment, we are measuring, the signal that we're measuring is excited minus ground. So the signal we get has an opposite sign from W. Okay, that's an important thing to notice later when you do the quantum tomography. When you try to analyze your data, that's like a detail you need to take into account, right? And and this is pretty obvious. This is the complex conjugate of that, and if you the sum of that is just the real part, and the difference is the imaginary part. Okay, so that's what U, V, and W means. Originally as an expansion coefficient of the matrix in terms of the Pauli basis. Now they separate. They can be expressed in terms of the matrix element, and of course, what you have here, right? The dynamical evolution of each matrix element can be used to find out the dynamical evolution of U, V, and W. Yeah? So the end result, the end result is this. Okay? So this is the end result. It may looks like a very by the way, the theta, here we define chi as chi amplitude modulus and with the phase theta, theta naught, okay? So that's what theta means here. If your coupling term is a real number, you don't need to worry about theta naught. All right, now, it looks like this is not easier than this. But this actually have a structure. If you take a closer look, V, W, U, W, U, V. Okay, this has a structure. Comparing to this has a more clear structure, and that is an outer product. So what is written here can be effectively cast into this form. All right. Okay. Do you see what this is? So here we define S equal to UVW, okay? So not a spin, but just like a vector. I'm just using it as a vector, using S as a vector. This equation can be simplified into this vectorial form. And this form is exactly the NMR equation. Okay? This form is exactly, remember, earlier I show you that the MMR is this, right? This has exactly the same form. Yeah. So you see, now you see that the UVW here actually correspond to the x and y coordinate of the Bloch vector. If you UV and W, well, it's actually is a good second. Okay, so how does UV and W connect to CG and CE? Because the Bloch vector was defined through CG and CE, right? So let's take a look. Okay, so this is 5, right?
In this equation, there will be term delta W, right? If you
Right.
F such that B as that vector, then there will be delta W term, right?
Delta W.
Does it look like in the cross product such a term will come, right? If we define B like that.
Delta W. No. Because here you have UVW, right? And this is BX, BY, BZ, right? And BZ is minus delta, right?
Okay.
So you won't get a product term.
Yeah.
Okay. Right. Okay. So UV and W are defined as rho in the rotating frame omega. So that's the prime. And if you want to go back to CG and CE, right, you need to change this to rho GE that, right? You need to do this. Yeah? Okay. And here we know this is CGCE star. CG CG star. Okay. Yeah. All right. So we know the CG is cosine phi, right? And C is sine phi with so this is that, right?
Isn't it better if you change that into 1 minus that first?
What?
We have EG square plus CG square plus CE square equal to 1, right? Use that to turn to only 1 time.
That's already including the cosine and sine notation.
Means in this step to change into just 1 term.
All right. This is so this term is cosine square. Sorry. Right? Yes? And this term is psi half. Yes? Okay. So, so this is also psi, okay? You see where this will go? You have the theta term out and plus. Phi and delta? Yeah, that's what I'm writing here. Yeah, I factored out the half sine theta. Okay? And this is minus this is 2 cosine. Right? And this is minus 2 sine theta plus delta t. And the minus 2 and this will cancel, right? So, you see that? So here we have U VW equal to, so according to this notation, this is psi. Let's just take this term as phi prime, okay? Just for simple notation. You see that? You see that? So this is the so this shows that this corresponds to this, and that is exactly the Cartesian coordinate. So the block, remember our question we start with is the black vector is defined by two angles, right? The polar angle and the azimuth angle. This is the azimuth angle, right? I'm sorry. X, Z, Y. Okay, this is the azimuth angle. The black vector is defined by the two azimuth angle. In this case, it is theta prime. Okay, and we want to find out the dynamics of the black vector and see if that see if the full dynamics, even including the excitation, correspond to the nuclear spin in a magnetic field. That's what we start off. That was like our initial goal. And to do that, we go through like a lot of math. And we finally reduce the Schrodinger equation into the equation, into this equation, this is called the optical block equation. We finally reduce it to the optical block equation. And we find that the optical block equation, the U, V, and W, can be expressed in terms of CG and CE. And if CG and CE, we use the block vector parameters to express CG and CE, then we can relate U, V, W to the two parameters of the black vector, the two angles of the black vector. And before we carry out the calculation, we don't know how the relation will look like. But now, after this, you see that the relation is the UVW is exactly the Cartesian coordinate of the black vector. Theta and phi are the polar coordinate of the black vector. But the Cartesian, if you transform this to the Cartesian coordinate, it is U, V, and W. Okay? So in other words, this equation of motion describes that is the equation of motion of the black vector. Okay? And this behaves exactly as the dynamics behave exactly as a nuclear spin in a magnetic field. All right? So that's the whole point of this derivation. This turns out to be a very, very useful tool. Super useful because everything about the dynamics, like whatever poles you apply, 1 or 2 or 3 or 4, you can use your right-hand rule and then you try to rotate the black vector on the black sphere as you would for a nuclear spin in a magnetic field. You don't need to actually solve a Schrodinger equation. Okay? So when you have, for example, a circuit diagram, a quantum circuit diagram which has like so many gates. How do you know what they will do? How does people know what these gates will do combined together to the initial state? What would be the outcome? How did they design this? Well, they use this tool. This tool is what gives them the confidence to predict what each gate will do to the state. Okay, so so what we talk about here is fundamental to quantum information processing. If you understand this, then you have nailed down 30% of quantum information processing stuff. Okay, all right. So that's that. Additionally, so some might say, well, if I am not, if I'm a fundamental quantum mechanics guy, I'm not too excited about quantum technology, I don't really care about quantum computation, like, is this still useful to me? Do I still need to go through the trouble of density matrix formalism and even go to the optical block equation? Do I need to go to do that? The answer is, for people who do fundamental quantum mechanics study, they need to deal with something called the open quantum system. Open quantum system is a quantum system that involves decoherence and relaxations. You have energy exchange with the environment. You also have coherence exchange with the environment. So that's why it's called an open quantum system. The tool to study open quantum system, the theoretical tool to study open quantum system, is not a Schrödinger equation, because Schrödinger equation assumes unitary transformation. That means the energy stays conserved. It is a closed system. Okay, but if you want to study the decoherence or dephasing or relaxation, you need to go directly. You need to deal with the density matrix, because in the density matrix you have the coherence terms, the cross terms, separate with the population terms. So you can deal with like dynamics that kill the population only, or the dynamics that kill the coherence only, because now they are like independently described. Okay. And if you can do that with the density matrix formalism, you can also do it with the optical block equation. And the nice thing about optical block equation, the advantage of optical block equation over the four density matrix equation, some people call it the master equation. The advantage of optical block equation over the master equation is that this has a very straightforward geometric interpretation. Okay, so you can like visualize how does relaxation does to your state, to your quantum spin. How does decoherence do to your quantum spin? How does dephasing do to your quantum spin? It's all here, right? So in order to include the coherence effect and the dephasing effect, you just need to add one additional terms on each equation, which is super easy. This, and this. Plus. Okay? Oh no. Oh, sorry. Minus. I'm sorry. Minus. So these are the phenomenological terms, by the way. So the coherence, dephasing, and relaxation are not in the standard quantum mechanics. They are just, phenomenons that we observed, and we would like to describe such phenomenon used within some kind of theoretical framework. So we add phenomenological terms like this to our standard unitary quantum mechanical equation. So these are the phenomenological terms. So with this, we can describe the dynamics of the coherence and relaxation on this Bloch sphere. Okay, this is usually called T1, relaxation time. It's called T. The reason this is called T1 and T2 is because this is identified as the longitudinal relaxation, and this is identified as the transverse relaxation. Why? Because if you take the z-axis as your principal, your quantization axis, as your, like in analogy to the nuclear spin, then the decrease of your Bloch vector along this axis, that's a longitudinal decrease. That's a longitudinal relaxation, right? On the other hand, the transverse plane, which is this xy, the projection on the on this plane, that represents your coherence, and the decrease of that is called the transverse relaxation. Okay, so that's why the Ty, T1, and T2 term are here. Okay, and there is one more thing, just as like a background knowledge, in case you, in the future, in case you study this subject. T2 has a theoretical maximum value of half T1. Okay, so T2 in principle can be very, very small, like the coherence can be very, very strong. But even in the most ideal case, you don't have the coherence. Even in the most ideal case, you don't have the coherence. This does not go to infinity. You won't have your coherence state indefinitely. Okay, this is bound. It has an upper bound by the relaxation, because you always have relaxation in the spontaneous decay. You always have that, right? So the theoretical upper bound of decoherence is half the relaxation time.
But why is it that 2? Is it because of the pi and the 2 pi?
No, that has to do with no. It does not have a very simple explanation. It has to do with let's see. A quick explanation. A very quick explanation is this term, okay? This term, if you square it, this term has, the coherence term has CG star CG star CE, right? So this is GG, and this is EE. Yeah. All right. So basically, there is a relation, sort of in its amplitude. There's a relation in the amplitude of the coherence. The coherence amplitude is related to the population by the square root. Okay. Now, if this is decaying, if this decays like this, right? No, sorry. If this decays like this and this decays like this, then together they will decay as gamma t. And the square root of that is, it will give you an additional half. That's where this half comes from, okay? And why is this? There is other derivation that is involved, okay? So, and these are explained. This is explained in Maloney and Elberly's book, Laser Physics. So that's in my reference list. So if you're interested, you can look into that. But but this is the theoretical maximum. So I'm just want to tell you that the loss of coherence is inevitable, one way or the other. Yeah? Okay? All right. Finally, we want to quickly go through the Hahn echo, which won't take us much time because now we have these tools.
I think we need a break.
Yeah, go for a break. Go for a break. Go for a 5-minute break.
So T2 contain both decoherence and dephasing,
Um,
or just decoherence?
Let me think. Give me a second. Let's see. T2 content, yes. T2 consists of decoherence and okay. So T2 consists of 3 things. Relaxation, which is the half, which is this. Relaxation and and decoherence and dephasing. All 3 of them are in T2.
T1 itself is the relaxation, right?
T1 is just relaxation, yes. Yeah. So that includes spontaneous decay or thermalization. Yeah.
So in this sense, we cannot distinguish between decoherence and dephasing, right?
No, you cannot. Right. Just by measuring T2, you cannot distinguish the underlying physical process. Yeah. That is rather unfortunate.
I wanted to ask whether, like I said in the presentation, was correct or not. Like,
sorry?
The EDU1, when I measured, like the Hahn spectrum just decreases like rapidly in the amplitude, and in the other one, like the amplitude doesn't change that much, but like it's symmetric in the presentation.
Are you talking about the time trace?
The Hahn spectrum.
The spectrum, okay.
Yeah, Hahn spectrum when we
As a function of frequency.
yes.
Mm-hmm.
And when we change the tau, like for the EDU1, it decreases and it shifts its Hahn spectrum when we increase the tau bit. And when I checked in some lectures,
okay, now I remember. I think you did 2 of them.
Yes.
And one gave a very
similar, like one was like EDU1 I had like this peak, but when I changed I had peaks here that's symmetric, but like it's not like symmetric about this axis. And ED2 was like if I had this peak is centered, the others are also symmetric, and the amplitude is also. This is ED2.
This is correct. This is wrong. I don't know what you did here, but when I took the Hahn spectrum, I have this with ED1
also. Yeah. Okay. I did multiple times because I did this and got the code, and I did the same thing. I was getting the same thing again.
Do you copy the code there?
Yes, but like
no, you cannot.
I mean,
there is a parameter in. So do you change it to?
I changed the parameters correctly.
No. The hardware on the 2 machines are different.
Yes.
So with this, EDU2, you have to use 0.5 nanosecond as a parameter. That's like the first parameter and as the time base, and this is 1 nanosecond as the time base. You don't know that, right? If you just copy the code.
No, I mean like the basic thing is like I did thing is the same, but I changed the parameters for the EDU1, the frequency, and all those things like for the EDU1. Not like exactly means. I'm just saying
but I'm asking you, does the code you run on EDU1 is that a copy from?
Yeah, but
from EDU2.
Copy as in the sense like all the functions and initial setup, but like the parameters I use are
Copy.
of EDU1. Yeah.
Copy means, do you get it from the local folder or do you physically copy the code from EDU2?
No.
Okay.
No, I mean like the initial the same setup I used in that. I used that.
I understand. You're talking about input parameters. Yes, you're talking about input parameter. I'm asking you about the code.
No.
But because the code on EDU1, the code is slightly like there's a slight difference.
No, I didn't copy the code as it is. Like I'm saying like the way like the Hahn echo and all the relations I used in the same. I did the same thing in this. So like to have not have like any code technical difference.
Okay. I don't know why you have that result, because when I run it, it gives me pretty symmetric. I mean, it's on my computer. I can show you. Give me pretty symmetric.
Because you mentioned T2 is the coherent time,
yeah,
and the maximum is 1/2 of the relaxation time. And how about the dephasing time?
Yeah, I'm not talking about this yet. And that's, in my opinion, this is a fake. This is a wrong physical measurement. I don't even want to even use it. I just think this is straight. This is wrong. There's in the hum echo session, we ask you to verify if this dephasing effect can be indeed corrected. There are like several experiments we ask you to do that and see if indeed it is that magical. You can, but just by applying another pi pulse, you can extend your T2 kind of indefinitely. And so far the result I have gotten says no. Okay, let me put it this way. Yes, I'm not saying that other people's measurements are wrong. I'm just saying that the interpretation, you need to be very, very careful on the interpretation of this. Okay? Because this is not as straightforward as what most people claim. This is not just like an extended version, like the maximum version of, if you correct for the phasing and blah, 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 then you have an extended version of T2. That's what you're talking about, right? And people call it T2 star. And you're asking me, can the extended version of T2 star exceed half the value of this? That's your question, right?
No, I just asked you to explain to me about the T2.
T2.
Yeah, for the dephasing.
T2 or T2 star?
T2 star.
Okay, T2 star, I will explain in the Hahn echo. T2 star is defined in the context of Hahn echo. Yeah, so we're not ready to discuss that yet. but we will soon. Okay. All right. So Hahn echo. All right. All right, so now I want to start with stating the problem. Hahn echo is a specific post sequence that is devised to battle with a specific problem. And I want to tell you what that problem is. Okay? So, and this problem is kind of universal. It exists in MMR. It exists in MV system, MV center system. It also exists in atomic system. Okay? But I'm gonna use MV system as an example since we're close to 5. So I want to do this as quickly as possible. Right? So we will not take a detour. We just start with the MV system. Start with the system that we have. All right, now we know that the MV center has different orientations, right? And different orientations correspond to different splittings, right? So if you have an orientation that is perpendicular to the external field, then your splitting is the largest. If you have an orientation that deviates from the static field, then your splitting is smaller. Your resonant frequency is smaller, right? All right. So that's now assume that we have a single orientation in the ideal case. We have a very, very good sample. And here, the orientation, the MV axis, which is represented by an arrow here, the MV axis is the same throughout the whole sample. Okay? What will happen if we perform an excitation on this ensemble? Because so far, a lot of things that we talk about concerns with a single qubit, right? What if we have an ensemble that are identical? In principle, they should do the same thing, right? However, in reality, we have spatial inhomogeneity in our static field. That is just unavoidable. We have a finite extent of our sample, whether it is 1 millimeter or 1 micron, or even nanodiamond, like a few hundred nanometer. We have a non-zero extent of our sample. And the field in that, however homogeneous it is, there exists a finite amount of non-inhomogeneity within that range. Okay? So, so say if this is B, and this is B plus a little bit delta B, and this is B minus a little bit delta B, right? Then here, here, so let me call this NV1, NV2, and NV3. Okay. Now MV1 and MV2 and MV3 will have a Zeeman shift that are very, very slightly different. A slight difference in the Zeeman shift. Okay? And that might not seem a lot when you think about excitation, right? So this is the excitation, and you have a Rabi pulse. Yeah? And this is your resonance. According to B. Yeah? And if you do this, if you do this again, if you do the scan, this is for MV1. Now, if you do the scan for MV2, then it's going to be a little bit shifted. It's going to be a little shifted. So this is MV2. For MV3, it is also shifted a little bit. Yeah? When you collect the signal, you're collecting an ensemble signal. That means you have just like a direct summation of all the symbols, of all the signals. It will become a big blob. Yeah? So this inhomogeneity on your spectrum, excitation spectrum, can introduce a little bit of broadening, but not a whole lot, because the shift is very, very small, very, very tiny, compared to your width. The width is determined by what? The transit time broadening, right? And also the power broadening. So this width is much bigger than this shift. So it doesn't matter a lot. But when you're trying to do coherent manipulation, then it does matter a lot. Okay? For one, you can see that for example, so this is Rabi spectrum. And so Rabi spectrum is 1 pulse. Ramsey spectrum is 2 pulse. In the Ramsey spectrum, we have very fine tooth. Yeah? The tooth is very fine. So when the center, if the center is shifted, for example, here, you see what could happen? Now, because our width is comparable to our shift, when we have like very narrow spectral width that is comparable to the shift, then the valley and the peak, the valley of one spectrum can overlap with the peak of the other spectrum. And the overall result is this. You lose your quantum coherence feature on your spectrum, right? So this this field in homogeneity matters a lot when you do coherent manipulation of your system, okay? And this is basically called dephasing. This ensemble effect, simply because the ensemble average your signal through different field values, local field values. So this causes an appearance of losing coherence because your fringe visibility is now gone. So it looks like, like a strong T2, right? That is called dephasing. Okay? Let's take a closer look of this. How does ensemble cause dephasing? Causing the so-called dephasing effect. Let's take a closer look at this using the block sphere. Now, I have, let me represent the 3 MV qubit as 3 quantum spins. Okay? And blue. Okay, so green is MV2, and this is MV1, and blue is MV3. Yeah? Yep, okay. Now, when I have a Ramsey pulse, what does the first pulse do? The first pulse turns this half pi, right? Yeah. Cause a half pi pi over 2 rotation, right? So it make this, it take this to the plane. Yeah? Now, you will only take this to the plane if your effective B field is on the y-axis. Okay? Remember, the effective B field has 3 components, right? The first 2 components has to do with the pulse durations and the pulse amplitude. But the third component has to do with your detuning. Yeah? So if you have detuning, means if the microwave frequency is exactly the same as your MV qubit oscillation frequency, then this is 0. And the B can be on the XY plane, okay? And in this case, it is possible to have it perfectly aligned with the Y, and this will cause a rotation of your quantum spin to the x-axis. Yeah? But like we said here, the the resonance frequency of all three of them are different because of the field inhomogeneity. So what is resonant to MV1 is not resonant to MV2 and MV3. Get it? Okay. So what happened is, for them, the effective B field will appear to be tilted. It will have a Z component. Okay? And there will be pole not on the equator, but slightly above. The circle that you trace out will not be this big circle. It will be like a tilted circle, because that circle needs to be transversed. That's the plane of that circle needs to be perpendicular to the effective B, right? And now the B is tilted away from Y. So of course, you will not be able to, after the standard amount of post duration, you will not be able to put this on the x-axis. Okay, so let me just say it is here. Sorry? Say it louder.
I mean, from the z-axis, we turn to the x-axis. And I mean, this component cause the rotation.
Yeah.
I mean, the effect. I mean, the x of v1. It should be x.
What are you trying to say? Are you talking about the direction of the B field? Let's now assume that the direction of the B field is in this direction, okay? It's in the minus y.
Oh, it's great. So for now, it's like the rotation here. For Lab2, it's just like the marble burst to meet to this axis. And the defacing is due to the external B field.
I couldn't get your point. I'm sorry. maybe talk to me later after the class, okay? Because we're on a tight schedule. All right. Let's now say that. Let's just be more specific. Let's do this. Okay. So the B field is on the minus xy axis, so the rotation is opposite to the B field, and you have this, and this is this delta is omega minus whatever your resonance frequency is. Okay, so for example, for MV2, your resonance frequency is this. Right? So if I make this resonant with MV1, that means I have a negative detuning for MV2. And a negative detuning means the field tilts up. Okay? The field will tilt up, and it will tilt up, and the rotation is perpendicular to this axis. Okay. So MV2 MV2 will be here actually. MV2 will be here, but not on this plane. It will be like a slightly above. And so this is for MV2. And the rotation for MV3, the effective B field for MV3 will go up, and you will put it here. Okay? But also above the XY plane. Right? So anyway, these are minor details. So what I'm trying to say is, first of all, what is resonant? What is resonant with one MV center is not resonant for other MV center. So the effect of the first pulse will put them in different positions. Okay, that's the first thing. Okay, and even if the frequency difference is very, very small, and these are like very close to this, okay, there is still yet another problem, which is the free evolution. Okay, so during this time you have the free evolution, right? And what is that going to I would love, okay. So everyone is going to process at their natural frequency, and it's going like this way. Yeah? It's going this way. Counterclockwise. Everybody is going counterclockwise. Some goes faster, some goes so despite of the difference in the initial position, the free precession is at a different speed. So your starting point is slightly different, and your free precession is a different speed. And because the free precession time is usually pretty long, so the difference in the precession speed make an even bigger difference than the initial difference in the starting position, right? So what will happen is is that this will go the fastest. So this is like when we look from the z-axis, they all go clockwise. Okay. Okay. So when the next pulse come, which is the next pulse is resonant with omega naught, right? So when the next pulse come, the next pulse will put this. So however long it rotates, the next pulse will be perpendicular. It's kind of hard to explain this, but anyway, it will be perpendicular to this, and then we will flip it to the south pole. Okay, so 2 pi poles, right? 2 pi over 2 poles. You'll flip it to the south pole. But what I'm trying to say is you can see that now here there is a big angle there's a big angle between this and the other spins. So that is effectively an initial phase added to your microwave pulse. And if you have an initial phase, what I'm trying to say is this same pulse will not pull the other spin, the other NV center to the south pole. Okay, so on average, the result is less. The signal is a perfect signal will be like the south pole, the excitation. But now you have like ensemble averaging from other NVs which will not go to the south pole. So your total signal on your total excitation now will be weaker. Okay, will be weaker. Okay. So anyway, so the point is to this field inhomogeneity will not only cause the rotation to different position, but mainly also it will cause the precession at different speed. And that's the main problem. Okay? That's the main problem. Because when we do coherent manipulation, there is always a gap time. So when they are like rotating at this plane at different speed, it is really hard to make them do the same thing. Okay? That's what I'm trying to say. So therefore, that is the problem at hand. And the Hahn echoes protocol, the Hahn spin echo protocol is invented to deal with this problem. Okay, so what is the Hahn echo pulse? The Hahn echo sequence is basically like a Ramsey pulse. Okay, so you have 2 pi over 2 pulse, but in between you add a pi pulse. Yeah, and why is that helpful? If we go into the rotating frame, okay, if we not just mathematically, if we like geometrically go into a rotating frame and rotate our observation point with at the angular speed of omega naught, then we will see that this omega naught will stay still, right? But this will continue to go forward since it has a higher frequency, right? So it will continue to go forward.
Around the z-axis?
In the clockwise direction. But this guy, because he's lagging behind, right? So you will appear in this rotating frame to go backward.
During the free precession or?
Free precession, yeah, to go backward. Okay. All right. So this is the lab frame. Lab frame. And this is a rotating frame. Okay. Now, what the pi pulse does is you will flip everything by 180 degrees around this axis. So that means this guy will go here. and this guy will go here. You understand? Okay, so this is y. I'm looking. So this is x. This is y. Okay, this is y. This is x. Okay. So there is a circle for this spin after the pi pulse, and the same with this. You'll get it here.
You switch the axis completely due to the pi pulse.
Huh?
You can say that you rotated your frame.
It's like a mirrored imaging.
Yeah.
Okay. Okay. So the pi pulse does this. After the pi pulse, the precession, the free precession continue. Okay. So whatever, if if this now this is going counterclockwise and this is going clockwise, right? So it was doing clockwise before the pi pulse. After the pi pulse, it still do clockwise, and this one still do counterclockwise. But if you wait for the same amount of time, this will go back to the minus x. This will go back to the minus x. All the spins will align together. Yeah? And then that spreading, that spreading due to inhomogeneity, the defacing will be gone at that instance, at that single instance. And after that, of course, the spreading will continue, right? But at that single instance, if you apply another pulse, then this pulse will have the same effect for all of them. Okay? So this wait time and this wait time are the same. Okay? So this will have the same effect on all of them. Comparing to just the regular Ramsey. This is a regular Ramsey. Here you have everybody pretty much aligned as the initial state because they are in the ground state. And after the pi pulse, they are put to the XY plane. Slightly, the positions are slightly different, but mostly the same, right? So you can still see them as like one spin. But after the free revolution, they kind of fainted out. So they are like a group of spins. But here after this, you kind of group them together. It's like a lens. This is like a lens. And they become the same. They become a single spin. And at that point, you apply another pi over 2 pulse, and they will have the same effect on all of them. Okay? And in the lab frame, it is in the lab frame picture. So the working principle of pi pulse is easiest explained in the rotating frame. Okay, but it is best understood in the lab frame. Okay, so here we say that they are like rotating all at the same direction, right? But this is lagging. This is like more ahead. Now the pi pulse will put this here. Yeah, we'll put this here. It will just do the same thing as this. You put this here, right? Now, you notice that the direction of rotation is still the same. All of them are still the same, right? So before the pi pulse, the MV2, runner MV2 is advancing. But after the pi pulse, runner MV3 is advancing. You put it in the front position. You put the slow runner at the, so this whole thing is like a track, right? This is a race track. At this moment, this is ahead. But after the pi pulse, you put this MV3 ahead, right? But this runs slower, and this runs faster. You put this MV2 in the back. This runs slower, this runs faster. So after some point, if you wait for some time, this will catch up. They all catch up, and they will, for one instance, they were all aligned. They will all overlap, right? This concept is the same as dispersion compensation in optics. In optics, you have usually you have, when you make a pulse, if you make a pulse, okay, this usually have a lot of spectrum, a lot of frequencies. And in the media, we know that the speed depends on the frequency, right? So you have the red, you have the blue. The blue usually travel faster. The red usually travels slower. So when you have a pulse that goes through a piece of glass, the pulse gets broadened because the red goes slower, the red component goes slower, the red photon goes slower, the blue photon goes faster. And that stretches out your pulse. Usually, in this case, we will use another thing that put the red component ahead of the pulse and the blue component in the back. We will switch their position, and we will let it evolve. And so the pulse initially was like this, and now after the glass, it will become like this, okay? And we will use another device called dispersion compensator. And after this, it will, after some time, it will become like this again. Because we put the slow runner ahead and the faster runner in the back, okay? So at one instance, it will become like a short pulse again. And at that instance, we can use this short pulse to probe our target of interest, okay? So this concept, this Hahn echo, spin echo concept, is very universal. A lot in other fields of physics, they use either optical dispersion compensator or RF compressor to do the same thing, to restore the sharpness or the narrowness of your signal. Okay, so I just want to say this is a pretty general technique. Okay, and why it is called echo, that has to do with the historical. It has some historical reason, because this method was first developed in the field of NNR, and in NNR they are measuring the signal in this plane, not the signal in the zeta axis. Okay, so when the spin comes back together as one, that produces a huge signal. So that's like an echo, like a copy from the origin. All right, so yeah, that's pretty much it. And the last remark I want to make is the same as the Ramsey. These are all coherent manipulations, right? These are all coherent manipulations. So all the pulses needs to be phase correlated. If you turn off the pulse completely and then start it again here, and then after that you turn it off and start again here, they always start with 0. They always start with the same initial phase. Then that wouldn't work. That kills the phase correlation between them, right? We talk about this phase correlation between pulses in the Ramsey interferometry lecture. Yeah? Okay, and another thing I want to say is that this method strictly will only work if the pi poles can do a 180-degree rotation. Okay? And this can do a 90-degree rotation. And this means that they need to be the poles that you use needs to be like exactly on spot. It needs to be resonant. If the poles you choose, all three of them are not resonant with one of the spins, okay? Then for all of them, you have this, this zip component, this tilted turn. And then all the geometry, all the arrangement will fail. Okay? So it needs to be resonant in order to have the 90-degree and 180-degree effect. All right? All right, so that's all about Hahn spin echo. All right. I bring my computer here today to show you the Hahn spin echo in the conventional NNR and also our MV center system. Okay. Let's get our quiz question done with first. And maybe as you guys pack, I can show you the data. It's pretty. And you will see that echo signal come out. So quiz question. Quiz question. Does echo only work for resonant Okay. All right. Let's not waste time. Please get up. And
in the first, when you say resonant excitation, is it of just one resonant peak excitation or just each excitation of any NV center will count? So it's like NV center, if we have 3 NV center, we have 3 resonant excitations, right? So we can take any one.
Okay, that question that is the question you think about. But for resonant excitation, I mean the 3 pulses. There are 3 pulses in the Hahn echo, right? So I'm asking, do they need to be, when you set the frequency, do they need to be set at the resonant frequency?
Yeah.
Okay.
Which resonant frequency?
Well,
means is it like for resonance frequency of total that we get, or like just of individual any?
I cannot answer that question for you.
That's the important thing you need to know.
Then that's the important thing you need to discuss. All right. So please stand behind the answer of your choice. Okay, we're still missing one person, but I guess we could just start the discussion. You can choose, so maybe you can partner with Tom and you can partner with Mustafa because you're from different groups, and we'll start the first round of discussion. Okay, let's please discuss.
I think you're wrong.
Resonant excitation and the
Section.
resonant excitation, like resonant frequency that we get if we just for one crystal that we do, the total means the main frequency that we get that resonant pulse, which one we do. So for the individual one, there are different and resonators we have. So this one, I think he meant for like the if we have 3 NV centers in the our diamond. The total one is what he says. The effective one is what he say, and for individual
Are you gonna choose yes or no?
I think it works for each individual one. I don't know.
No?
That's why
Okay.
I said like.
I'll be your discussion partner. You're wrong.
You're wrong.
You're wrong.
No, but during your presentation you talked about that the thing is but the excitation. I mean, I thought the initial states, right? They are not all like in the same axis. So what
In the
is-
initial state,
Yeah, in the initial
the
state.
initial state is always ground state, right?
Yeah, but what we said is like the initial states for the three, for like the different receptors are a little bit spread out. So I thought,
Most of them
What do you
will be
mean?
around here.
Spread out.
I mean like
The frequency, the resonance frequency are
yeah, the
different,
resonance frequency is still
but the
same
spreading
for all.
out is not.
It doesn't have.
It's not in the initial,
If I use
right?
omega
The
1,
initial,
I can get
they have the
plus
same
1 here. If I
orientation.
use omega 2, I
We're
can
assuming that
get
they all
second
have
one
the same
here.
orientation.
If I use omega 2,
Yeah.
I can
Yeah,
get
and
third one
the
here.
slight
It's not just one
frequency
resonance.
difference is due to the
I can use
homogeneity of
different one, but all of
the
them
field.
will be like-
Because
have
initially,
But they start with the same ground state.
I mean,
They're
all
all,
going
all
upwards,
yeah.
more or less. But we said, of course, we're not going to be completely aligned upwards.
That's what I.
Of course, they're gonna be outward because they are cooled down to
That's what
the ground state.
Is it?
But one that was we're talking about the good thing about the Hahn is even if they are a little bit like off,
When you are doing this,
you pull them down
But why would they be
in
off?
the spinlab,
again.
what
Why would
we
they be off?
take as resonance
Maybe it's not
frequency
perfect.
of the
Of
whole
course,
diamond.
it's perfect because it's ground state.
When we do the spectrum, we get the
No, but
frequency
still,
for the
it's
whole
not
diamond of
perfect.
the LGS.
Why?
Then this is the maximum, this
When it's
frequency
not like
This is the ground state.
resonant frequency.
Yeah, but it's like
That's
the
not for the
magnetic.
individual ones.
It depends like.
But if you change a bit,
The ground state has
But
nothing to do
material
with
is
the.
not
ma-
homogenetic.
That's
It's not like an isolated system.
So you understand? That's
No.
what I asked him.
The
Is it
the
ideal
the,
one
the
or is
cooling
it this
depends on
one?
the optical pumping, right?
Yeah, yeah, yeah.
And that works for individual of them. So even the frequency individually are different. It doesn't matter because the cycling is with respect to its own energy scheme. So all of them will be in the ground state.
Yes. But on the blocks we're not exactly in the same direction.
Of course, it's the same direction because they are all pointing up. That's the ground.
But then we do the poles, the first poles, and then we say we're going to separate, right?
That's another. Yes.
I
That
thought it was because we are not entirely in the same direction in the beginning, but no.
Yes.
What causes them to fan out then? It is if not all of them go to the equator,
Yeah, I think one of them is
and if not all of them go to the equator,
if one of them is going to, for example, here,
a little bit above the equator.
right? Then you will just free process at here,
Yeah.
right? And if one of them go a little bit downward, it will free process here. They're just free processing at different planes.
Yeah.
Yeah. Okay.
But is that what causes them to fan out?
What causes them to fan out?
It has to do with the quote, like the subtraction, the difference.
Are you sure? I think you're wrong.
All
All right. Okay, great. Good. I see like a very furious discussion, and that's good. Okay.
Is it
looks like we might need a second round of this discussion. All right. Does anybody want to switch your answer? So we have 4 no and 1 yes. Woo! God, man, good. All right, let's have another round of discussion. All right, this time, just try to, maybe you can talk to Musfa, and then you'll talk to her, and you can talk to me. Okay? You're wrong?
Okay.
Of course, because you choose no.
Yeah, switched.
You were wrong.
Yeah.
The correct answer is, of course, yes.
I was still thinking that at first, yeah. So I was thinking, okay, resonant excitation, we've got to have the right frequency in order to shift this distribution of the states. Right, so it's like if you have a totally off microwave frequency, it wouldn't affect the states, the distribution of states at all, right? Because it won't have any effect at all. But then I was thinking, okay, what does actually the Hahn echo mean? And you know, we get the like, okay, we're gonna have like 90 degrees, then 100 degrees, then 90 degrees again.
Right.
And the degrees is just like the time it takes for the distribution to change from halfway from one polarization to other polarization. So I was okay. Then I realized that the number of degrees is not dependent on the frequency being the right way. It's dependent on the time being the right way.
That is a key. That is a key. Is that so? I challenge you on that.
I think so. Because if you have off frequency, you get
you feel like, okay, let's put it this way. If you have an off resonant excitation, right? You think with enough time you could achieve 180-degree rotation.
It will affect less of the distribution.
No, just for, if we talk about just a single spin, single MV, and you have an off resonant excitation, you think just with enough time you can go to the South Pole.
To an extent, yes.
Is that right? Think about it. Because in order to go to the South Pole, your rotation plane needs to be in the YZ plane. But if your rotation plane is not in the YZ plane, can you still go to the South Pole?
Yeah, sure. I don't see any correlation between the YZ plane and the frequency being different.
Of course, there is a relation because your rotation plane is perpendicular to your effective B field.
Okay.
And the effective B field depends on the detuning.
That is just a matter of our reference frame. I mean, I can. The global phase doesn't affect the states. I can just rotate the whole blob sphere, and I will still line up my XY plane with the axis it will rotate on.
You're talking about you're talking about the angle, the initial phase of the pulse. The initial phase of the pulse, of course, will change the axis on the XY plane. But what about Z?
We remove that effect.
What determines the Z?
It's okay that it's off resonance, but when it comes to the
you mean of state vector?
No, the effective B field.
It should be the alignment of the crystal in the field.
If you remember that formula, do you remember the formula?
No.
I hope you do.
Which one?
The effective B.
Which one?
The optical block equation.
Yeah, the S
Cross effective B, right? And the effective B has XYZ component, right?
Yeah.
And the XY component has to do with the characteristic of the pulse, like the pulse duration or the pulse strength.
Yeah.
But the Z component,
But how does the frequency or the detuning effect
You get the maximum
affect
at
The Z component. The Z component is the frequency detuning. So in other words, if you have an off-resonant pulse, then your rotation axis is tilted from the XY plane.
Okay.
We think like
that you need to think about, and that's why you're wrong.
even if it's not
You're wrong, believe me. You are wrong, and you're wrong, and you're wrong, and you're wrong, and you're wrong. You're all wrong. All right. Okay, guys. All right. Cut it out.
Even without that.
Oh, okay. Everybody make up your mind. All right. So I think 2 rounds of discussion is all we need. We don't need more because we're running out of time. Anybody want to switch? You want to switch to no, or you want to switch to yes? Anybody want to switch? Anybody want to switch? Count down. 5, 4, 3, 2, 1. Nobody want to switch? All right. Does Hahn echo only work for resonant excitation? It says yes. You're right. Okay. Can the pulse in a Hahn echo sequence start with the same initial phase?
So can we explain it since 4 of us didn't understand it?
Okay, well let's first get the second question.
Okay,
yeah. Then if you want to go to the lab, you can go to the lab. You want to stay and here I explain it, you can stay, okay? But let's get the second question out of the way, okay? All right, so for the second question, if you want to choose yes, stay on this row. If you want to choose no, stay on that row. Can the pulse in the Hahn echo sequence start with the same initial phase? Yes or no? Okay, now we have Tom on the yes side and Simon. So 2 versus 3. All right, cool. I will have Tom debate with Mustafa, and Phoenix and Vida and Simon, 3 of you will debate. Okay?
You think I'm wrong?
Yeah, I think you're wrong.
Okay.
He mentioned that
but isn't
the
it
sequence should each pulse
Start with
should have,
the statement, you're wrong.
Yeah, so you have
phase coherent, not the
initial
exact
phase
same
on the
phase,
top
but
of the
coherent.
water, right? You go down.
So
Not
it's like
necessarily,
you
but yeah. We often do.
In our
have the
example,
pulse,
it's easy to think in.
you have something like that. But the next pulse shouldn't start at exactly.
And then you have a mirroring.
Should be
Yeah.
something like this.
I think it depends on all the pulses. I guess.
Exact coding every time. He said that. So that means like.
But what's the definition
I
of
don't know,
initial?
but usually.
It's just where you start when you send the pulse. Yeah.
You at different position on the
So
indicate display,
it
but
can-
as like
do we usually
I don't know how to say this word. It says a name. I mean, you have
Oh, I'm sorry.
So
Mute.
But initial phase
How does it have
the
anything to do with it?
position of
It's just that-
vacancy or of the pulses? Well, I was thinking when you say like initial phase, you mean like this is a microwave pulse. It's like here. So if this is initial phase, but you're talking about the particles.
20 seconds.
Does the can means like we usually do, or can that be possible? Because like you can make the pulse like that, but it's not like what we usually do. So is the can means whether can
If you do it like that, what kind of effect will they produce?
yeah, it will not have like phase coherence since it has same phase.
What?
You said we need to have like phase coherence between the pulses.
But I thought he was talking about the microwave pulse.
I don't know. Don't ask me. Ask him. I'm not your discussion partner.
I think the initial phase of the pulse is irrelevant.
No, exactly. That's the thing. So it's not
So you should switch to our side. Exactly.
But it depends. Like when you're asking about the initial phase, you mean of vacancy centers or of microwave pulse?
Microwave, of course.
Yeah. If you're talking about
Can the pulse, the microwave pulse, start with the same initial phase?
No, he's not talking about the vacancy pulses.
Okay.
So aren't you wrong?
I
then?
still say they don't matter.
But can start with initial phase? If it doesn't matter, then you should answer yes. Then you can start with the same, right?
Should I? Is it just like a matter of phrasing, or should I just say should?
Yes. Yeah. That's
Okay,
better.
is that better?
Pulses of
Yeah.
Okay.
Should the pulses of a Hahn echo signal start with the same initial? Not necessarily, right?
Yes.
Yeah.
But I mean, I guess we can. I guess we can, but okay.
Yeah.
Should.
All right. Okay, let's see. Anybody on the switch side? Are you sure? Are you very sure? Do we need another round of discussion? You think? No? What do you think? Do we need another round? Are we sure?
We're sure.
Okay. Well, then should the pulse, can the pulse? The answer is no. Correct. The answer is no. All right, so very quickly, you can start to pack, and I just want to show you two pieces of data, one from NMR and the other from our MV center. And I want to show you the echo, where the echo is, to give you like a visual. So this is a device that we use in the modern physics lab. It's an NMR device. And this is the data. This is the data from the device. You can see that when you first excite the system, it has a strong peak, right? And that peak sort of fall apart after some time. This is the ensemble dephasing, okay? And then after, I think here, yeah. Sorry, this strong peak is not the signal. This is the signal. Okay, the height, it starts from here and it drops. And this is another pulse. This is the pi pulse we apply to the system. And after we wait for the same amount of time, the signal comes back, right? To be at the same level as this. So this is like an echo. Echo, like a copy of this. Okay, that's the Hahn echo in nuclear resonance. This is what I use. This is data from our MV system. And I use quantum state tomography to take this data. This is the Z component. This is the U component, the black. And V is the Y component. So U and V are on the XY plane. So they are the coherence one. And you can see initially I have a strong coherence here. And after some time, that coherence drops because the fanning out. The fanning out, the averaging makes it drop. But after I apply a pulse, which is here, marked by this line, after some time, that signal comes back, but it is on the other side. Remember, when it comes back, it is not on the positive X, it's on the negative X. So that's the Hahn echo. in our MV center. That's pretty cool. This is a quantum. All right, so that is.
So the wireless is you know like.
Huh?
How about the wireless?
The norm. Oh, sorry. The norm is the not just the square root of all three of them. I didn't show that. Okay, that one doesn't matter. Yes.
Why the V signal change before you give a pulse 300 nanoseconds?
Okay. I guess that's the extent of my pulse. Yeah, I guess this is the extent of my pulse. Yeah, I forget exact. Like my pulse is around here, and I have a finite extent. My pulse is about, I think 100, like about 100 nanosecond. So it could be from here to here. Yeah, I think it is from here to here. Yeah. Yeah.
I was thinking about the black, the U data. Is there a kind of echo on the right side here? Because I see some like symmetries. Like here, it's a little bit above the zero line. It's a little bit below the zero line. Is it just noise or
I don't know. I think it's probably noise. Yeah. On the black sphere, you can see I start from here, right? And the first pi over 2 poles pull my black vector to the equator, right? Now, afterwards, this goes towards the center. Why? Because I'm measuring an averaged V, not individual V, right? So when they fan out, the average V goes down. So that's what I'm measuring here, right? And when I apply the, so this position is where I apply the pulse. When I apply the pulse, the fanning out spin start to focus, and that's why this grows. Okay, that's why this grows. And then after that point, the fanning out will decrease the total V signal again. Yeah, but the U, which is in this direction, should be, because it is the fanning out is symmetrical around U. So U should have no component as a result throughout the whole process. So I think this is just some kind of noise that I don't understand. Yeah. All right. So this revival, this kind of bring back your coherent signal. That is Hahn echo. Okay. And if you're so concerning this first question, if you don't have if it is not resonant, then I want you to remember, this is very important. The first two component has to do with the pulse strength and pulse duration. But the third one is strictly just detuning. So if you're using an off-resonant pulse, okay, so say it is like above Y, then your spin will, so this will become.
We're talking about the first pulse now, right?
Any pulse. I'm just about. Okay, so your rotation plane is no longer XZ, but it is tilted. Okay, but it is tilted, and then when you are rotating on this plane, you can never reach the South Pole. It's very important to remember that. And this also this point also reflect. Remember when we have Rabi oscillation, if you have an off-resonant pulse, it will not only affect your periodicity, but it will also affect your height. Remember? Okay. So the maximum height, that is the South Pole. And so when you have off-resonant, you can never reach that maximum height. And the reason is your rotational plane on the Bloch sphere is, it's tilted. So it's like here.
Yeah.
You never reached the true south. Okay? So you never could do a true 180-degree flip. So if you're, and of course you can try to achieve a 90-degree rotation, but you can never do a 180-degree rotation. So Hahn echo will only work for resonant pulse. That means in the Hahn spectrum, remember, if you take the Hahn spectrum it looks like this, right? Only the resonant point, only the central point. This point is where the Hahn echo could work. If you deviate your pulse, the 3-pulse frequency from this value, it wouldn't work. Yeah? Yeah. So that's just something to keep in mind. And also there are other limitations. So it only works for resonant excitation, that's one limitation. It doesn't correct for any excitation, all excitation skin. Second is your inhomogeneity needs to be small enough. If your field inhomogeneity is too strong, so say if you use like a bar magnet as your static field, and that has like a very strong dipole, gradients, and over your sample, and that gives a very large spread on your frequencies, right? In that case, even a Hahn echo cannot bring back the spin because the initial position is different on top of the different angular speed. Okay, and also the effect of 180 will not work because the 180-degree rotation will not work because the deviation, the off-resonancy is just too big. Okay.
My question, because like you said, the Hahn echo, of course you have the fanning out of the different vacancies, right?
Mm-hmm.
What caused the fanning out?
Because each of them have a different free precession frequency due to the field inhomogeneity. So some in the left frame, they all go clockwise, but some go faster, some go slower. In the rotating frame, the slower one will go in the reverse direction, and the fast one will go, still in the clockwise direction, and that's why it looks like fanning out. But either way, if the difference in the distribution in their frequency is too big, then the Hahn echo will not be able to save that.
So if we take an individual frequency of 1 NV and if we put that's not the resonance of the whole system,
yeah,
we will not get this Hahn echo.
No, that's the whole point. Because you cannot have that's the whole point of Hahn echo, because you cannot have a single frequency source that works for everybody. So it is unavoidable that this field inhomogeneity will cause a fanning out.
Yeah, the fanning out will be there, but when we do when we are taking the effective on that one, yeah, if I took the slowest one as that, so everything is traveling fast. But when I did the 180 degree with that frequency, the slowest one will flip exactly as that, and the other one will be at the side. Then if I take the same time, it should come back to the same place, right? Any of the individual frequencies.
The red. So okay. If you tune your microwave frequency to the slowest one, then it wouldn't work. It needs to be tuned to the center of that distribution.
But like in theory,
If you need to go to the lab, feel free to do so. We're done here. Huh?
We need dinner and we go to a lab afterwards.
Yeah, sure.
So if it's the slowest, then this is the slowest I did. But when I do 120 with respect to this will come this.
Yeah.
So if this when the other with the same time, it should in theory get in the same place with the pi parts. If this is the reference frequency that I'm taking, it doesn't matter whichever
Okay.
it is, because
Let me see. Okay.
so that's why I was thinking if for any individual frequency that we take, it will go. It should work. Not only the middle one. From this picture, I don't know whether any other complications are there.
Okay. I think. So if you do it with the fast one.
Yeah, first one, everyone will be slower. Everyone will be behind this coin. Then if I project this will get here itself.
Yeah. Yeah. So your question is by resonant. Which one do I tune this into? Which is taken as the resonance? That's your question. That's your objection.
Yeah, my objection is like
Yes.
I understand when we take the resonance one, like we can get the Rabi oscillation and take the maximum frequency as the resonant one. That's the one you meant by here. But even if you take any individual one, which is like slightly different in this case, we should also get that. That's my point. It doesn't only work for this particular one, but any individual one.
Yeah.
In theory.
Okay. So I agree. So first of all, I agree with what you mean. So say this is your spectrum. This is a single MV spectrum. And typically the deviation, whether this is the slowest one or the largest one, doesn't matter. Typically the deviation is very, very tiny. Maybe like, I don't know, a thousandth of the width. Okay? So this is typically very, very small. Maybe like 100 or 1,000. Okay, the distribution. So you're right by saying, yeah, I could place this anywhere and it would still work. For me, the resonance, when I say resonance, I'm thinking about this and this. The difference. I'm thinking about like close to the width of the spectrum, which is much larger than the spread. So you're right. I could have some tolerance, and as long as this is within the distribution of the field inhomogeneity, it's fine. But if it's outside of that, then it wouldn't work because nobody can do a 180-degree rotation, right?
Yeah.
And that's why I'm trying to go with this question.
That's why.
I see your point. So there's a loophole in the question I ask. Yeah. So maybe I should say for.
So everyone was thinking in terms of individual frequencies.
I don't think so.
No, we were talking about that.
I think only you understand that this symmetrical thing will work for.
We were talking about that with others.
Okay. And all of them agree here?
Not all of them, like me and Simon was talking about this. Me and Phoenix talked about that, but she was like, okay, you meant all of the individual resonant, these are all resonant frequency individually. So she said, okay, that may be the thing.
Okay, maybe, okay. All right, I see. Maybe I should say very small deviation.
Yeah, that's
how should I say, how should I phrase this? Very
in the vicinity of resonant excitation. When you say, means when most of the time when you say resonant, you mean like a particular frequency or that, right?
Yeah. Okay, but what I wanna wait, okay, maybe I should.
In the bandwidth.